Hello everyone, my name is Mustafa and today I will present my final project titled Machine Learning and Molecular Descriptor-Based Classification of Environmental Pollutants with Analytical Platform Recommendation. Current literature confirms widespread contamination by PFAS, microplastics, and biomass-burning products, while researchers also report difficulties in resolving complex pollutant source signatures. Therefore, this project investigates whether machine learning and molecular descriptors can provide a faster and more intelligent classification strategy. The objective of this project was to construct a complete computational workflow for environmental pollutant classification. First, a curated dataset of representative pollutants from 5 environmental sources categories was assembled. Second, molecular descriptors were calculated to numerically represent chemical behavior. These included molecular weights, which reflects compound size, X-log P, which indicates hydrophobicity, TPSA, or topological polar surface area, which relates to polarity and transfer behavior, hydrogen bond donor and acceptor counts, which describe intermolecular interaction potential, and rotatable bond count, which reflects molecular flexibility. Third, these descriptors were used to train and compare multiple machine learning algorithms. Finally, the optimized model was applied to classify pollutant sources and recommend suitable analytical platforms such as proton transfer reaction (PTR), gas chromatography (GC), liquid chromatography (LC), all of them coupled with mass spectrometry (MS). The first step of the project was a literature review to identify representative environmental pollutants from scientifically reliable sources. I selected compounds reported in books, review papers, and peer-reviewed journal articles covering atmospheric chemistry, PFAS contamination, PHs, polycyclic aromatic hydrocarbon oxidation products, VOC, volatile organic compounds oxidation products, biomass burning emissions, and microplastic degradation markers. This ensured that the dataset was based on real environmental relevance rather than random chemical selection. For the next step, and after reviewing the literature review, I manually curated representative compounds and assigned them into 5 pollutant classes: pH oxidation, VOC oxidation, microplastic-related compounds, biomass burning markers, PFAS compounds. Each class contains molecules with different structures, polarity, molecular weights, and functionalities. This diversity was important because the machine learning model needed to learn meaningful chemical differences between pollutant sources. In total, the final dataset was contained with 87 compounds. After selecting the compounds, I used Python to automatically retrieve molecular descriptors from the PubChem database through its REST API. And the code is showing in front of you, so it is like a summary for the whole code that I wrote it. So it can go and it can retrieve the descriptors of each compound in PubChem. For each compound, the script sent an online request and extracted descriptors mentioned before. These descriptors transform chemical structure into numerical variables that can be interpreted by machine learning algorithms. Before model training, I performed a complete quality control scan of the dataset using Python. I checked dataset dimensions, class distribution, missing values, summary statistics, descriptor ranges. The results confirmed that the dataset was balanced across pollutant classes, had no critical missing values, and showed strong chemical diversity. This step is essential because reliable machine learning always begins with reliable data. In this step, I used Python libraries including pandas for data handling, matplotlib for plotting, and seaborn for statistical visualizing. In this step, I used then box plots were generated to compare molecular descriptors across pollutant classes. Each figure was automatically saved in high resolution for reporting and presentation. Graph 1 is the first descriptor analyzed with molecular weight. PFAS compounds showed the highest molecular weights indicating larger and more complex structures. VOC oxidation compound shows the lowest values consistent with smaller atmospheric oxidation products. The second descriptor was X-log P, which represented hydrophobicity. PFAS compounds display the highest X-log P values indicating the stronger hydrophobic behavior. Volatile organic compound oxidation had lower values showing more polar character. The third descriptor was TPSA, which measured molecular polarity. VOC oxidation compounds generally showed the highest TPSA values due to oxygen-containing functional groups. Exploratory analysis, I applied principal component analysis or PCA to reduce the dimensionality of the dataset while preserving most of the chemical information. First, the numerical descriptors were selected. These variables were then standardized using standard scalar because they exist on different numerical scales. Next, PCA transformed the 6 descriptors into 2 principal components, allowing visualizing of hidden relationships in 2 dimensions. Finally, I generated a score plot and a loading plot to interpret the results. For the PCA score plot, it shows how compounds are distributed based on their molecular descriptors. We observed partial clustering between pollutant classes, meaning some sources share similar chemical properties while others are more distinct. PFAS compounds tend to separate from the other groups due to their unique size and fluorinated chemistry. This indicates that molecular descriptors contain meaningful information capable of distinguishing pollutant sources. The loading plots it will explain which descriptors drive the separation. Molecular weight and X log P contributed strongly in one direction, while TPSA and hydrogen bonding descriptors contributed in another direction. This means both molecular size and polarity were major factors influencing compounds classification. Overall, PCA confirmed that the datasets contain structured chemical patterns supporting the use of supervised machine learning models in the next stage. Meaningful structure in the dataset, I moved to supervised machine learning. The molecular descriptors were used as input features, while pollutant source categories were used as target labels. Several classification algorithms were tested, including tree-based models, support vector machines, distance-based methods, and probabilistic models. To ensure robust performance evaluation, I used 5-fold stratified cross-validation, where the dataset is repeatedly divided into training and validation subsets. This allowed fair comparison of model performance and reduced bias from a single train test split. This comparison shows that the decision tree model achieves the highest mean cross-validation accuracy, making it most suitable classifier for pollutant sources prediction in the dataset. And to recommend the analytical instruments, I created a rule-based function using molecular descriptors. Lower molecular weight and moderate polar compounds were assigned to PTRMS. And here it's good to note that PTRMS is a soft ionization, so the compound or the pollutant won't fragment while detecting them. Moderate size hydrophobic compounds and high volatile compounds were assigned to GCMS. Larger or more polar compounds will be assigned to LCMS. The heat map summarizes how different pollutant classes were distributed across predicted analytical platforms. VOC oxidation, pH oxidation, biomass burning, and many microplastic compounds were mainly assigned to PTRMS, reflecting the presence of smaller detectable compounds. PFAS compounds were predominantly assigned to LCMS because of their larger size and stronger polarity. This can confirm that different pollutant sources may require different instrumental strategies and that molecular descriptors and compounds behavior or pollutant behavior can predict the needed instrument to be detected in it. To evaluate real-world performance, I tested the selected decision tree model on 2 completely independent unseen datasets, each containing 10 new pollutants. In the first validation set, the model achieved 80% accuracy. In the second validation set, performance increased to 9% accuracy. At the same time, each compound also received a predicted analytical platform, recommendations such as PTR, GC, or LCMS, based on molecular descriptor rules. Across both external tests, the average predictive accuracy reached 85%, demonstrating robust generalization. This strengthened confidence that the workflow captures meaningful chemical source relationships rather than memorizing the original dataset. The workflow produced promising results. Several limitations should be acknowledged. First, the dataset size was relatively modest, containing 87 compounds, which may limit model generalization. Second, some pollutant classes share overlapping chemical properties, making classification inherently challenging. Third, the instrument recommendation system was rule-based rather than experimentally validated. Future work could include expanding the dataset, integrating advanced descriptors such as Redkit fingerprints, testing more powerful algorithms, and validating prediction using real laboratory measurements. This workflow could evolve into an intelligent screening platform for environmental analysis. This project demonstrated that molecular descriptors can be successfully combined with machine learning to classify environmental pollutants according to their probable sources. This work represents a first step towards smarter, faster, and data-driven environmental pollutant identification. Thank you for listening. Bye bye.